All right, in our last lecture, we talked about numbering systems that are used in cybersecurity, and we did a little exercise in base 64 encoding. And somewhere in that process, we talked about MAC addresses, which were hex codes, a series of hex codes, and we talked about how the MAC addresses are used within an Ethernet subnet to address our traffic and send the traffic within its self-contained subnet. And that's great if we want to send data between devices that never leave our network segment or our subnet. But it doesn't work so well if we want to send data across the internet. We need a better scheme for that. And so today we're going to talk about IP addressing. And even though we talked about MAC addressing in conjunction with the local area network, the network segment, keep in mind that we were still using IP addresses, and remember the ARP message we sent out, we talked about the ARP message is who has this IP address, and then whoever has that IP address responds and say, I own that IP address, and here's my MAC address so you can send traffic to me. Well, now we're going to look at that IP address part. And so we're gonna talk about this, and it looks like I need to move my screen over a little bit. So let me adjust here. There, that looks like you can see it. I got several windows open here, so I'm going to shrink these other ones down. We'll have to move them as I get further in the lecture. So, when we talk about IP addressing, if we just talk in general about what an IP address is, an IP address is a number that's formatted in dotted decimal format. So we have 4 sections of the IP address, and each of those sections represents 8 binary bits. So I pulled this chart over from our last lecture where we had the powers of 2, 2 to the 7th down through 2 to the 0. And we have the numeric values of each of those powers of 2 here, and if you add them all together, they come up to 255, which is why the maximum number you can ever have in any dotted decimal section of an IP address, the maximum number you can have is 255. You can never go over that. So, we have an IP address, and this tells us 2 things, this IP address. It tells us the network that the system is on, and it also tells us the host ID, or the host address. So how do we know how much of this is the network and how much is the host? Well, you remember when we were talking about MAC addresses, I put a nice little line down the middle and said the left half belongs to the manufacturer of the card, identifies the manufacturer, and the right half identifies the card serial number, essentially. Well, we don't do the same thing in IP addresses. This line is very movable. Whatever's on the left of the dividing line identifies the network, and whatever's on the right identifies the host IP, but this line could be here, could be over here. It moves, so we have a varying number of bits that identify the network portion versus the host portion of the IP address. So if we have a varying number, how do we know what that number is? Well, we use another component in conjunction with the IP address, and that's called the subnet mask. And the subnet mask is going to be in one of 2 formats. We see it in either dotted decimal format, or we can see it in binary. And so let's look at an example of each one of those. So let's say that one thing I could have is 255.255 224.0.0, and that's my subnet mask. And if I break that down into binary, remember each of these dotted sections is 8 binary bits. So if I do this in binary, this first one is 255, that means it's all ones. So that was easy. The next one is 224, which is 128 plus 64 plus 32. I think that's going to give me 224. You can check my math if you want. And so then the remaining bits are going to be zeros. And the last two are going to be all zeros. And so that's the same subnet mask in binary. One thing you'll notice about the subnet mask is always, 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 it will have all ones on the left that identify the network, and where the network starts and the zeros start taking over. That's the host portion. So that's how we know how many bits belong to the network ID and how many belong to the host ID. The ones are always network bits, the zeros are always host bits. So the same communication, or the same information, is communicated in this format. Again, when we look at these numbers, when we break them down in their binary equivalents, they will always break down so that we have all ones on the left and all zeros on the right. So in this case, I have 8, 9, 10, 11 bits that identify the network, and then the remaining bits, there's 32 bits in total, 4 8-bit sections. So 32 minus 11 leaves us 21 bits that identify the host. So with 21 binary bits, I have a lot of combinations here, which means I have a lot of hosts that can go on this network. And we're going to look at how we determine that here in a minute. So that's the basic structure of an IP address. And you always have to know not only the IP address, but the network mask, because if you don't know the subnet mask or the net mask or the network mask, you don't know how many of those bits are network and how many are host, and it makes a huge difference in what you're really addressing. So with that, I'm going to move into the way we used to do IP address assignment. We used to, in the early days of the internet, going back to the 1990s or so, we used a scheme called classful IP addressing assignment. And what we would do is when somebody wanted a network, we'd ask them, do you want a big network, a medium network, or a small network? And if they wanted a big network, we'd give them a Class A. If they wanted a medium network, we'd give them a Class B. And if they wanted a small network, we'd give them a Class C. But there's actually Class D and Class E networks, but they're never used publicly. They're only for testing purposes. They're reserved for different things, so you'll never see Class D and E used. A Class A network, I said, was a bid network. I guess a more technical term would be a large network. And what we do is we identify Class A networks by some fixed binary bits. From the highest order, which means starting over here on the left-hand side, the highest order bit in a Class A network is always 0. The rest of them will change, but the first bit is always 0. However, the bits that identify the network in a Class A network are the first 8 bits. So whatever's in this first 8-bit section here identifies the network. We can never break it like we did here at 11 bits when we're doing classful addressing. Classful addressing always breaks on the dots in the dotted decimal format. So Class A breaks at the first dot, Class B breaks at the second dot, Class C breaks at the third dot. How many hosts can you have on a Class A network? I'm going to let you look that up. I gave you that as a question on your assignment for this. But I'm going to just tell you that it's in the millions range. So every Class A network has millions of hosts available in it. Most organizations don't need that. There's only actually 126 Class A networks, and one of them is private that you can't use on the public internet. So we really only have 125 of these worldwide that we can work with. And so they're very limited, and they're all spoken for. They belong to large ISPs, companies like AT&T or Deutschcom, companies like that. So even your smaller telecoms don't have a Class A address. And all the Class A's are spoken for. That's a problem. And typically with these telecoms that have these Class A's are actually selling chunks of that Class A to other smaller telecoms, who then in turn sell it to their customers, who might be another even smaller telecom, and eventually you get to buy an IP address from somebody that owns some IP address space. The dotted decimal range, the first section for Class A networks, they don't, even though we break it at the first dot, we don't get all of that first section for Class A's. The Class A's only range from 1 to 126 in that first dotted section. So everything from 127 on up is not a Class A. And we'll see that here in a minute, how that works. The 10 network is reserved for private addressing. So you could use the 10 network internally in your organization for traffic that doesn't leave your organization, even if it travels in a WAN, so it goes through a router to another subnet in your organization. You can configure your router to route private addresses in the 10 range. You can do that internally in your organization, but they will never be routed outside your organization. Routers on the internet will drop any incoming traffic on the 10 range, so you can only use it within your organization. And that's what we mean by private addressing. This is reserved for private addressing. The net mask for a Class A network is either, if we do it in dotted decimal format, it looks like that. 255 in the first section, meaning all ones, if we break it down into binary, and everything else is zeros. So I'm not going to break it down into binary because it's pretty easy to do that. So those are some characteristics of Class A networks. Again, remember this first bit is always 0 in the actual address, not in the net mask. The net mask is going to be all ones. And remember, every time you see an IP address, you need a combination of the IP address and the subnet mask, or the net mask, to figure out what it really means. So now let's look at Class B addresses. Class B addresses are medium-sized networks, are medium-sized pools of addresses. the fixed binary bits from the highest order. In Class A, we just worried about the first bit. In Class B, the first 2 bits of the IP address itself will always be 0, 1. The bits that identify the network in a Class B are the first 16 bits. The number of hosts, whereas in a Class A we had millions, in a Class B we have thousands. And the dotted decimal range for Class B networks goes from 128 to 191. So don't get this confused. Just because Class A's are based on the net mask being this, all ones in the first portion, Class B's still are identified, Class B networks are still identified in these first 8 bits. It's the difference between the IP address itself and the net mask. So these first 8 bits for a Class A go from 1 to 126. For a Class B, go from 128 to 191. Notice I skipped over 127. I'll talk about it in a minute. It's a special network. The private address range for Class B networks goes from 172.16 to 172.31. So what this tells me, this is one network, 172. This 16 tells me that 172.16 is my first private network, 172.17 is my next private network, etc. So I have 32 private Class B networks that I can use internally in my organization or for testing purposes. So there's 32 of these that are reserved for private use and can't be routed across the public internet. The net mask for a Class B network is always this, meaning that if we were to break it down into binary, the first half, the first 16 bits would identify the network, and the last 16 bits would identify the host. So that's what we see in a Class B network. In a Class C network, these are small networks. And the fixed binary bits are the first 3 bits. They will always be 0, 1, 1. And the bits that identify the network are the first 24 bits, meaning only 8 bits are remaining to identify the host. Consequently, since we only have 8 bits to identify the host, and we know we've seen this 255, which is 8 bits, and that's the maximum number you can have in binary with 8 bits. So we should know that that's going to be actually 255 minus 1, and I'll explain why that is in a little while. We actually end up with 254 hosts, or I should say, to make it consistent with the others, hundreds of hosts in a Class C network. And again, this information is readily available on the internet. I ask you questions about it in the assignment that accompanies this lecture, so you'll be able to find that fairly easily, I think. The dotted decimal range, or the first section of the IP address for a Class C network, ranges between 192 and 223. So we had 1 to 126, 128 to 191, and 192 to 223. The private IP address range is the 192.168. Yeah, let me do it this way. It's this whole 192.168 range. So we can have lots of Class C networks. We can have 255 of them because this whole section here from 1 to 255 can be the third part of the network address, and then each one can have hundreds of hosts defined here. So we have many Class B addresses or Class C addresses that are private that we can use internally and for testing. And the net mask is 255.255.255.0. And if you were to break that down into binary, we would have 24 ones and 8 zeros. And that's the way we did addressing up until early in this century, when we started to exhaust our available IP address. So IP addressing was a US-centric thing. The US companies own most of the IP address space. Foreign countries struggle to get public IPs that they can use in IP version 4, which is what we're talking about. And so a movement came about to conserve address space. And what we found is that lots of organizations were purchasing, say, a Class B network with thousands of available hosts when they only had a couple of hundred of hosts on their network. And so they were wasting a huge chunk of IP address space. And it's not cost effective either, because you pay a small fee every month for every IP that you lease. You don't own them, you lease them. And so the cost to register an IP address and lease an IP address is generally somewhere in the $3 to $5 per month range. And so you don't see that when you lease an IP address from your ISP, because it's built into your monthly service fee for your internet service. But it's there. You're actually paying for the IP address. And even better, you don't get to use it all the time. You share it with other users on the same system. And you'll get assigned an IP address dynamically every time you connect to the internet. It may be different from one time you connect to the next time you connect. And we might look later in the course at how we do that. But for now, the important thing to realize is classful addressing is outmoded, outdated, because we need to conserve available IP address space, and so we needed a different scheme. And we're going to talk about that different scheme here in just a second. But before I do, I don't want to forget to go back and talk about that pesky little 127 IP address range that we skipped over. 127, we call that the loopback address range. It's essentially reserved for testing. If you open a web browser and put in the IP address 127.0.0.1, that refers to your system. There are other ways we can refer to your system, but that's one way. Another way we can refer to your system is by putting in the URL localhost. That will also look at your system. So if you were running, say, a web server on your local system and you wanted to access your own web server, you could access it with either localhost in the address bar or with 127.0.0.1 in the address bar. You always have those available to you, at least if you haven't changed the default configuration that your system comes with. So that's what the 127 range is used for. There's other testing that we do with other IPs in that range, but that's the most common use, is to do what we call local loopbacks and refer to ourselves. So that's why the 127 range is not a public range either. So with that in mind, let's pretend that we did not go in our time machine back to the 1990s, and we want to see how we really do IP addressing in our current environment. So I put an IP address here, an example IP address, and I just picked a kind of random IP address here, but I've added something to it. I've added this /18 to it. You notice when we're talking about classful addressing, we never had this /18 part. And that's because we knew that the network was identified based on the class, and it broke at the dots in the IP address. But to conserve address space, we said let's use as many bits as we need to give the user the number of hosts that they need IPs for on their network. Instead of saying, oh, I need 260 IPs, so we say, well, there's not 260 available in a Class C, so we'll give you a Class B, which has thousands of addresses. We don't want to do that. We say, what you need is a little more than one Class C. A Class C is 8 bits. If I give you 9 bits of host address, that's going to more than cover your systems. I still have to break it at powers of 2, but I can be much more efficient using classless routing, where I don't break at the dots, than I could with classful routing. So classless interdomain routing, you'll hear it called CIDR, or some people call it CIDR. So you'll hear it expressed those different ways. And this slash part tells us how many bits identify the network. So in this example here, if I have 18 bits identifying the network, that means there's 32 bits total. So if I take 32 minus 18, that leaves me 14 bits to identify host. Still a pretty good size network. So how big is if I look at this subnet mask, let's look at this subnet mask and see what it is. So maybe I should just copy this whole thing here, and we'll fill it out again for CIDR. Fixed bits. There are no fixed bits in CIDR. We vary them as we need to. Bits that identify the network varies depending on what this slash number is here. Number of hosts varies. Dotted decimal format, first section, could be anything. Private addresses, we still have to respect all Class A, B, and C. Private addresses. Just because we switch to CIDR notation, CIDR assignment, doesn't mean that we can suddenly route those Class A, B, and C private addresses. So we still have to respect those. Net mask. Well, we can't really say because it's not a fixed net mask. In the example, we have a /18 up here. So what that means is we would have, well, I'll tell you what, I'm not going to do it in binary. I would have 18 ones and 14 zeros. But let's do it in dotted decimal. The first section is going to be 255, that's 8 bits. The second section is going to be 255, that's another 8 bits, that's 16 bits. So I need 2 more bits. In the third section, the leftmost bit is 128, and the next one is 64, which means that this section, the dotted decimal, would be 192, and the last one would be 0. So we know what the net mask is based on this slash number here. And so this is what we use now to assign the amount of addresses we need. So typically what will happen is when you go to an ISP and say, I need to lease some IP addresses, they're going to give you an IP address with a slash number that identifies your network range. The problem is, in a large enterprise, they're going to give you enough IPs to cover your whole enterprise in one block, you hope, if they have it. They may not have it to give to you. They may have to give you several smaller blocks. But typically, they would give you one contiguous block of IP addresses. And that's great, except that big blocks of IP addresses are notoriously hard to manage. Keep track of what IP address is assigned to what system. So a common tactic in organizations is to break those IP addresses down based on functional areas. So we take our large block of IP addresses and we say, I want a network for my sales staff, and I want a network for my accounting function, and I want a network for HR, separate from accounting and separate from sales, and I want a network for my R&D staff. I don't want people in sales jumping the gun and talking about our products that are under development before we're ready. So I want to keep those separated, segmented on separate subnets. So how do I go about breaking that IP address space down into smaller segments? We call that subnetting. And so what I'm going to do is walk you through an example of how we do that. And so I have an address space here. Make sure it's up on the screen where you guys can see it. I don't think I can get it any further to the right. I think that's as far as I go. So we might have to deal with some minor formatting issues here. Maybe I can zoom the view out just a small bit. There, you can get it all on the screen. So, looks like I can maybe go up just a little bit. No, I'm not going to, because it's going to cut off the right-hand side. Hopefully that's readable to you. Let's assume that we've been assigned a network address of 142.224.0.0/13 by our ISP. So first, let's think we're not going to subnet it. Let's figure out how many IP addresses are available on this subnet that the ISP leased to me. So I have 13 bits identifying the network, which means the other 19 bits are available to assign to host. So I need to do 2 to the 19th power to see what my number of host is. And if I bring up a calculator and I do 2 x to the y power 19, I come up with 524,288. However, the actual number is going to be this number -2. -2 for every unique subnet that we create. So my number is going to be 524.288. Or 286, I'm sorry, -2. And you might say, why -2? The answer is the very first IP address in a subnet is used to denote the subnet itself or the network itself. So there's no rule that says we can't assign that to a host, but we've been doing it this way for decades, and it's become convention that we don't assign that first IP address to a host. We reserve it to refer, if we're creating documentation and we want to refer to the network by its IP, we use the first address to do that. We could buck tradition and assign the first IP to a host, but for all purposes in this class, we'll assume that we're going to abide by established convention and reserve that first IP address to identify the network itself or denote the network itself. Also, the very last IP in a network range is used as a broadcast address. So sometimes we want to send a message to all 56 hosts on our network. And rather than typing in 56 different IP addresses as the addressees of the message, we just use the last IP address that says, hey, everybody on this network, this message is for you. And so it's a broadcast message. And again, that's a convention. If we absolutely don't want to do broadcast messages, we could assign that last IP to a host. But we're going to assume, for all purposes in this class, that we will never assign the broadcast address to a host. And so we will reserve it, and for every network we create, we will subtract 2 from the power of 2 that identifies the number of hosts. So in this case, we end up with 524,286. So what's the binary representation of the network address? So the network address is this portion right here. Of course, this is the network. And so we don't have to worry about this number of hosts right now. And so what we want to do is break these numbers down into binary. And so what we do is we start with 142, and we look at our powers of 2 from the other document that we did. Nope, not that one. The top of this one, we use these powers of 2, and we say, for example, in the first one, we say 142. Can I subtract 128 from 142? Yes. So the first bit, the 2 to the 7th power bit, is a 1. And I subtract 128 from 142, and I'm left with 14. Can I subtract 64 from 14? No, so this bit's a 0. This bit's a 0. This bit's a 0. I got 14 that I'm working with. I can subtract 8 and 4 and 2, so those 3 bits are 1, and the last bit's 0. So if I go back now to the other sheet, I could put that in here. We had 1, 0, 0, 0, 1, 1, 1, 0. So that's what 142 is in binary. I can do the same thing with 224. 224 is a 128 plus a 64, which gives us 192 plus 32 gives us 224. So the next 5 bits are 0. And the last two dotted decimal sections are all zeros. So that is our binary equivalent of the network address. What is the network mask or the subnet mask? I intentionally use different language in different parts of the assignment to make sure that you get exposed to all the terminology that you might see. So what's the network mask for this network in both binary and dotted decimal format? So in binary, we have 13 ones on the left-hand side, broken into 8-bit chunks, so there's 8, 9, 10, 11, 12, 13, and then 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. That wasn't hard, was it? And in the dotted decimal, the first section here, we can look at the binary, the first section here is going to be 255. And the next section is going to be 128 plus 64 plus 32, which was 224, plus 16, which is 240, plus 8, which is 248. And then the last two are going to be 0. Don't get confused between the 224 here, because 224 is a common subnet mask, but that's part of the IP address. This 248 here is based off of this /13. So now we know what the net mask is in both binary and dotted decimal format. So now we're going to actually say, let's break this 500,000 IP addresses into some smaller, more manageable chunks. So, how many hosts could we put if we divided our network using 2 of the host bits and making them into network bits? So we're using 2 host bits to define subnets. And if we do that, how many subnets could we define? The answer there is, quite simply, it's a power of 2. If we have 2 bits, there are 4 combinations. We could have 0, 0, 0, 1, 1, 0, and 1, 1. So we could define 4 subnets if we used 2 host bits to do that. What would the net mask be? And I'm going to do this one in binary first. And it's going to start off the same as we had above, but then we're adding 2 more bits. A common way we denote that we're using bits for subnetting is, rather than put a 1, we'll put S's, and then we put, let's see, I got 7 there, so that's 8. And so that would be our binary net mask. And another common thing we do if we have color in our documents is we'll make those in another color so they stand out, and we say, okay, we're subnetting and we have 4 subnet bits. If I'm going to do this in decimal, dotted decimal, I guess I should say, to be clear, what we do is we simply add these bits to our total. So before we had 248, and these bits, it's the third one from the right. So this bit has a value of 4, and this bit has a value of 2. So we're going to add 6 to 248, and we do that, we get 254. So we get 255.254.0.0. And that's our dotted decimal format. There's not an easy way to show the net mask, the subnetting bits in dotted decimal format. How many hosts could we have on each of these subnets? And the short answer is we take this number, and since we're making 4 subnets, we divide it by 4. So if I take that number and do the -2, because I didn't do the -2 earlier, and then divide it by 4, I'll get a strange number. I can't have a half an IP address. So typically, we're not going to do it that way. We're going to do (524 to 88) divide by 4 equal 131,072, and then we take 2 off of each of the subnets. So the answer would be 131,070 for each subnet. So if you're doing it and you're getting fractional IPs on each subnet, you're doing it wrong. You can't ever have a fractional IP, number of IPs in a subnet. So we have 131,070, which is still a really huge network, but that's what we decided to do. So now the question becomes, what are the parameters of each of these subnets? So for every subnet that could be created, list the subnet address, the range of host addresses that could be assigned within the subnet, and the broadcast address for the subnet. And we can probably guess the very first subnet is going to be this number here. That's if your ISP is nice to you and gives you the IP address at the start of your IP address space. They don't always do that. Sometimes they will give you an IP address in the middle of your IP address space. And then you got a little more work to do to figure out where your address space begins and where it ends. But if you use any number of online calculators and you put in an address in the middle of the space, it will normally figure out what the whole address space is. So for now, we're going to assume that this is our first subnet ID, or the IP address of the network itself. I already forgot what it was. 142.224. And we know, once we have the network identified, the very first host address is going to be +1 in binary. So it's going to be 142.224.0.1. Now comes the tough part. What is the ending host address and what is the broadcast address? Well, if I take that 142 and I break it down into the network section and the host section, what I'll see here is I have 17 bits allocated to the host section right now. And these 2 bits are my subnetting bits. So I'm going to mark them in a different color. Actually, that'll be ugly. So those are my subnetting bits. So I have to figure out with 17 bits what this number is. Well, this number, if I made it all ones, is going to be 255. And this number, if I made it all ones, is going to be 255. But over here, I just have one bit to deal with. And the rest of these identify the actual network. So I got to kind of go in reverse order and figure out what these bits are. So these bits, if I made them all ones, would be the end of the network. Actually, these bits, if I made them all one, would be the end of the network. So I have 128 plus 64 is 192, plus 32 is 224, plus 16 is 240, plus 8 is 248. I don't want to actually use these two bits right now because I'm in the first network. In the next network, I'll increment one of these bits to a 1, this first least significant bit to a 1, and that'll identify the next network. So if I did that, the next network starts at, the first section is going to be 142. The second section is going to be whatever, 1, 2, 3, 0, 0, 0. The next network is going to have those bits as its network ID, which means 128 plus 64 is 192, plus 32 is 224, plus 2 is 226. So this second section equals 226. So that means that the first section is going to go from 142.224 up to 142.226. And so if I go back to my next, or to my chart here, this one, I just figured out that this one is going to be 142.226.0.0. And that's going to be 142.226.0.1. Once I know that, I can work backwards into this one and say this one is 142.225.255.255. That's the broadcast address. Because if I add 1 to this in binary, it becomes this number. And then if I subtract 1 in binary from the broadcast address, I'll get this address. I have to get my 225s and my 255s straight. And so that would be the last IP address. Once I know the pattern of my subnets, it's just going to repeat. This one's going to be 227. .227 again. And I could do the rest of this just to get you started. This one's going to be 228. And the last network is going to be 230. And that's our 4 subnets. And I could fill the rest of this in, but I'm not going to take the time right now to do it. So I could fill out that whole table and figure out what the practical, useful information is as I'm assigning IP addresses to things. That's a little bit tedious to have to go through this whole process of figuring out what the next network is when I increment in binary and figure it out that way, but I can do it. A better way might be to use an online calculator. And so what I'm going to do, take this IP address here, and I'm going to show you a couple of different online calculators. And I'm going to post these in Canvas for you, the links to these. And we also need to make note of our /13. That's going to be important when we use these online calculators. So here's one calculator. And this is like the first one that comes on if you Google online CIDR subnet calculator. By the way, if you're using a subnet calculator, there are a lot of classful subnet calculators and classless CIDR subnet calculators. Make sure you're using a CIDR calculator when you do the assignment. If you use a classful calculator, you will crash and burn and get all wrong answers. So, I put my IP address in here. That's my network. And then it asked me how many mask bits, and I know the answer to that is 13. So I put in 13. Hey, guess what? It tells me I have 524,286 IP addresses. So that matched what we had with no subnetting. Now, if I want to subnet, I simply change the mask bits to, by the way, notice this address range right here. This is the entire range for our unsubnetted IP space. Goes from 142.224 to 142.231.255.255. If I change this and tell it that I want to have 15 mask bits, this particular calculator, what it does is it says, you have 131,070 IPs available for use on that subnet. And what it does is it just shows me down here at the bottom the very first subnet out of my 4 subnets. It doesn't show all 4 of them, it just shows you the first one and says if I show you the pattern for the first one, you should be able to figure out the rest. So it shows us that our address range goes from 142.224.0.0 to 142.225.255.255, and that matches what we put in our table in the assignment. So we've got good data there, and we could use this subnet calculator, provided we give it the right inputs. It might be better if we had another subnet calculator that would give us all of the subnets. And so here's another one, online calculator. And again, I'm going to put my IP address in here. And you got to look at these and read the instructions and figure out what you need to put in here. So, for example, in this one, I have to put the CIDR notation net mask. But I have to put the unsubnetted net mask, what they call the major network address. So I don't use 15, even though I'm going to end up with 15, I use 13. And then I have to manually, this is kind of a pain, I have to manually put in the size of every network. So I know those are 137 or 131.070. And by default, there's 6 networks here. But I only want 4 networks, and I know that. So I can change this number here, number of subnets, to 4 and click change. And when I do that, it takes away those extra blocks, and now I only see A, B, C, D for my 4 subnets. It still hasn't told me what the size or what the parameters are for those subnets. The reason I'm doing /13 up here is because this 4 is telling the calculator to turn that /13 into a /15, because 4 is 2 bits in the net mask. So now if I click on submit, I'll get this table. Let me move this over a little bit where you guys can see the edge of it. and then I'd probably make it a bit, no, I can't, maybe I just leave it there. You can see enough of it. You can see the first network has 131,070. The network address is 142.224.0.0, which is what we had in our table. The assignable range is from 142.224.0.1 to 142.225.255.254, which is what we have in our table. And the broadcast is 142.225.255.255, which again is what we had in our table. And the same thing, we can see the next address, the next subnet is 226, the next one is 228, and the next one is 230. So these online calculators do work. The problem that you run into with these online calculators is that people don't always put the right inputs into them. Let's say you put something different. Let's say, for example, your ISP, instead of breaking on a major break in the IP address range, so I think the next one below 224, if I use a /13, I think the next one below 224 is actually a 216. But let's say that our ISP wasn't nice to us and they gave us something in the middle like 221. And let's see if this would work and what it would give us and whether or not it would throw us off. Is our first network now going to be 142.221.0.0? Let's see what happens. You can see it changed automatically. It said that's in the middle of an IP address range. So it automatically changed it to a 142.216, which is the beginning of that block. It changed it for you. So it handled that pretty well. And then 221 is actually somewhere down here in this in the middle of this third subnet. But that's okay. Now let's look at another thing that can go wrong. Let's say that you've said, I'm going to use 2 bits for subnetting. So you put the 15 up here instead of the 13. Now let's see what happens. And you still leave this at 4. Notice it's given us a subnetting failed message, and it says you're trying to use, because you said each IP address, each subnet has 131,000 IPs, it says you're using 400% of the available space that you have. And so it's telling us that I could define one network, the first network, that worked, but I can't define these next 3, they're shown in red, because I don't have enough IP addresses, because I entered my inputs incorrectly. So you need to make sure that when you're using one of these calculators, that you enter the inputs correctly, and you can come back and refer to this video if you're having problems with that. And so those are 2 online calculators, free to use, no registration, etc. There's actually another calculator that I really like to use when I'm doing subnetting. It's called the SolarWinds Advanced Subnet Calculator. It's a little different. It's not a web-based calculator. It is a Windows application. So you have to download it and install it on your machine to use it. It is free, and you can Google it. I'll give you a link to it as well. But keep in mind that if you can't install apps on your computer, you're not going to be able to install it. The school may not appreciate you trying to do that. Also, in order to download it, you have to fill out a registration form. You have to give them your name and phone number and email address and some other stuff. There is no checking on the form. You could put all bogus information in there and it sends you to the download. But you do have to, they do ask you to register, so keep that in mind. It may not be worth the hassle. It's a lot slicker than these web-based ones that we've looked at today, and it will give you all of the subnets, and it will give them all to you in a exportable format, So if you were trying to document your network, you could simply copy and paste them all from the calculator into your network documentation, which is really, really great. But you do have to register. And SolarWinds as a company, they manufacture their own networking tools. And so the reason they want you to register is so they can send you some marketing info on other tools that they sell. So anyway, that's out there. I'll send you a link to their webpage, but you might want to stick with the web-based calculators. They do work if you give them the right inputs. They're just a little less intuitive than the SolarWinds calculator. And so what I'm going to do, I'm going to save this completed. I'm going to go ahead and fill out these last two rows here, and I'll save this completed in-class demo and post it for you on Canvas. And then I'm going to post an assignment in Canvas for you. And what I want you to do, it's very similar to this. And what I want you to do is do that whole assignment and submit it. And I'm setting it up to where it should auto-grade and tell you what you missed as soon as you submit it, because you'll get a worksheet just like this one to fill out. But what I want you to do is actually type them in. I'm creating a quiz in Canvas that has the same answers as the worksheet. Oop, that didn't work. I'll just type them in manually. It's not that much. It has the same questions as the worksheet, so if you do the worksheet, then type them into Canvas and it'll give you some instant feedback on whether you're doing it right or not. But you have to complete the first worksheet, or the whole worksheet first, because I'm not going to give you more than one attempt to take the quiz portion and enter your answers. I want you to do it all in one block, and it is graded. So take your time with it and make sure you get it right. I don't want you to wreck your grade on the very first assignment before we even get to any real hands-on labs, which we are going to do later in the semester. So take your time. Subnetting doesn't come natural to a lot of people. And so I want you to make sure that you get it right. Yeah. And I think that's all I'm going to do for today. I'll get this posted for you, and you can refer to it and watch the video if you're having trouble doing the subnetting. But take your time with it, make sure you get it right, and at the end there's some very easy questions on the last page about classful addressing, which I even answered some of them for you, but I deliberately tried not to address all of those questions in the lecture, but I gave you hints about them. And so that's all for now. Good luck with subnetting exercise, and next time we'll start talking about what are the major issues in cybersecurity these days, who are the major actors that we need to worry about, and the kinds of bad things they're doing. And we call all that information the threat environment. So it's very important as a cybersecurity person to understand the threat environment that you operate in. And so that's what we're going to do next, is kind of set up the environment that we operate in and the threats we're facing, and then we'll talk about how to combat those threats.